All right, guys. So this is the last module before the unit test. I might do. Oh, this one doesn't have a unit activity. So yeah. So we're just gonna go over what we can do with these. So what we can do with exponential models. If you guys don't remember what exponents are from algebra 2, let me turn on my pen real quick. So the idea of exponential models is if we have a function related to y that has some number that we multiply it by, then a base and an exponent that goes to it. So what happens here is these are always going to grow like this, and they have an asymptote, meaning that they never touch a certain point. So they get really, really close to zero, for example, but they never actually touch zero in theory. Does that does everybody remember exponents? Have any questions about them? Yes, that is what an exponent is. That little number on the top. That is the exact definition. More importantly, that little number on top tells us how many times we're going to multiply by that specific number. So if we have like b to the like 8, it's going to be b times b. Why did I pick 8? That's a really big number. 1, 2, 3, 4, 5, 6, 7, 8. Now I regret picking 8. So that's what an exponent is. And because it's multiplication, that's why it grows so fast. It's multiplying as opposed to like when we were doing lines, all you would do would be adding a different number. So if you had 4x, technically every x you were adding 4. So that's how come it grows so fast. So looking at this, when we're trying to do a laboratory experiment, in this lab experiment, let's no, actually, we're just talking about cooling down coffee, not messing with chemicals. So, what we're going to do here is you have learned coffee. Right, I'm going to obtain a hot cup of coffee. So, in this one, we're not. We're we're not gonna actually do the experiment. It's more to understand exponential decay. So I'm just gonna find something on Google that kind of tells us what we're doing. Oh, actually, if you do not have access, this is what we're gonna do. So I was I was gonna say we were gonna just look it up, but they're literally giving us the numbers. So is there a way I can just they're not letting me copy just that column. Nope. Stop it. Yeah. Oh wait. I think if you do it here though, oh well. Well, we're just gonna use these numbers for now. So, well, I don't have to type it in, but when you guys go back, rewatch this video or whatever, just make sure to enter this onto your Edmentum. And all right, so here, what we're gonna do is we're gonna want to graph this. So you can use whatever tool you want. I can't graph it, but basically, if I wanted to, I'm going to use my little pen here. So at 0, it's 100 degrees. So at 0, we're going to go to 100. At 15, it's 85.8. Oh, well, it looks like this. So what's happening here? Okay. Well, what you can do is just use a little pencil, kind of like what I'm doing here. Except since I'm not a student, it's not letting me edit it. But you can just grab this pencil, put a little dot here, I'm gonna pretend to do it with my actual pencil that lets me write on the screen. Put a little dot, put a little dot, dot, and you'll see that it kind of makes this little curve. And just do it as best you can. But it should end up looking like this. The main idea with exponents is it has a really fast rate of change. So if you look at the slope between this point and this point, it's really big versus here where the slope is going to start getting smaller and the slope is going to start getting smaller. So what's happening is this is an exponential decay. It starts decreasing at an exponential rate. So here, does the decrease in temperature look linear and exponential? We're going to say exponential because the rate of change keeps decreasing exponentially. So it's going to be like it looks like it is exponential because the rate of change keeps decreasing. If it was better, so if it was a linear function, the rate of change would be consistent. So it has the exact same slope all the way through. So that's why I brought up slope. All right. And what else? So self evaluation, just grade your guys' self on how well you knew about exponents and stuff like that and how slope had to do with exponential decay or lines. That's what I recommend you guys evaluate yourself on. That way, you guys know like what you might need to work on or study in the future. So here's the form that I was talking about, where this little a right here affects like how fast we grow. In other words, this little a, if we have zero right here, because anything to the zero power is one, if we have a, b, x to the zero, this would just be a, meaning that our x value is zero and our y value is a. So that's where they get this point right here. Also, if we're dealing with a negative number, that's why it says less than one, a negative or a fraction, this is what causes exponential decay. The rate of change is decreasing, so we keep getting smaller and smaller and smaller. Cool. That's a good thing. You should have learned this in algebra 2. And another thing, guys, is this p is known as our principal. So that's how much we start off with, and that's why it's always here at the 0 point. All right. So if we're doubling $1,000,000, then our base, our b, is 2. So that's how come in this thing of doubling, our base is 2, and then our t is the amount of time, and this n right here, I believe it's n. Let me double check. I want to say it's t divided by n. Oh, t times n. N is how many times it's compacted in that amount of time. So let's say we were talking about 1 month. If we're talking about 1 month of compounding, but we were talking in terms of a year, then it happens a twelfth of the time. So it's 1 month times 12. Does that kind of make sense, guys? That's how come they have a fraction right here, because it's compounded less than one time. So even though it's supposed to be n times t, the n represents how many times it's compacted. So for a month doesn't get compacted. It only gets compacted a twelfth. So here, now we're talking about they're compacting. So we're talking about corona is a virus, not a bacteria. So we're not talking about corona. So what's happening here is this virus keeps doubling, and it doubles, it looks like T amount a day. So in other words, every 10 days is the amount of time it doubles. So where is it? So every 10 days. So in 5 days, it it only happened one time. So that's the only amount of time it compacted. In 15 days, it's 1.5. So that's why it's 15 over 10. Is this making sense? So you always want to look for this when you're talking about your rate. All right. And then moving on. So if we're talking about doubling a population of 750,000, and it doubles.
Oh no, what is happening? Hello?
Can you guys hear me okay? Can you guys hear me okay? Sorry. Yes. Hello. Woof woof. Is it still going slow? Can you can you guys hear my voice on time at least? Better. Okay. Okay, as long as the audio's fine. All right. So we're starting off with a population of 750,000. So this is going to be our P. Our N is going to be this 36. But more specifically, it happens every 36 years. So it's 1 over 36. Or in other words, T divided by 36. Does that make sense? So using the formula doubling with the population for a city in 4 years. If the current population is this and the doubling rate is that. So what we're going to do here in terms of P naught and T and D, would you solve the problem? Would you use the equation, use the keyboard? So when we're talking about this, we're going to set this up as P equals P, and we want a subscript of this 0 to make it P naught. So we're going to hit this little subscript, or you can hit Control down, Command down if you're on a Mac. And then our doubling rate, so we're going to do 2 exponent. Oops, that is not the exponent one. Exponent. And it's going to be T. More importantly, make sure it's a fraction. T over 36 in this case. So they actually gave us a population starting point. So this would be equals to 75,000 because we know what our P naught is. Parentheses 2. I'm going to raise the exponent. Oops, that was supposed to be a fraction. Fraction 4 divided by 36. And let's see what Admentum actually wants for the answer because it's usually very picky. Of course. So they just want this top part right here. And they want it of T. So you have to do subscript T. So they didn't want you to actually plug in all the stuff. At least this one wasn't like the inverse one where I like calculated the whole thing. Yeah, they didn't want the 30. Yeah, they didn't want the 36. They literally just wanted this and a doubling formula. Does that make sense? All right. And this one, they actually want us to plug it in, I think. Now you can use proper notation, input the values. So this one, we're going to input the 36 4 years. And here, we're going to change this to 7,500,000. What's up?
Oh, sorry, my friend sent me a message. I just died. Look at the message. It was just a picture.
Oh,
Sorry, continue.
I forgot to put the 4. So that's all they wanted. So they want all this. Make sure you fill out everything, unlike me. And technically, this should be a 4 as well. I don't know why Momentum isn't like I feel like Momentum's picky on certain things and not other things. But P of 4, so P after 4 years is this. At Momentum wants you to put it down like this though.
Yeah, it was really weird.
It's
Momentum stupid.
it's very picky with this. I'm sorry, guys.
Yeah, because when you like look it up, like you actually try to do it, it like tells you something else. And like Edmonton's like, nah, you're already wrong.
Yeah, that's why in the unit activities, make sure to let me know when you get the unit when we do unit activities. Make sure to let me know that we have plenty of time to like look over it because Momentum's probably like the answer key usually tells me that it's wrong, and then I'll look at it. I'm like, they put it down right. All right, so here they're just telling you with E. So this is about continuous growth. For example, sometimes things grow continuously, like for example like bacteria. It is nice to say that like bacteria will double every so much years, but this formula with an E, this tells you how to do it without kind of like going into the little details and stuff like that. Does that kind of make sense?
Yeah.
So for example, instead of doing like, oh, it grows by 25%, instead of having to do 1.5 as your base and then doing your n over t or whatever they have, or I'm sorry, t over n. I don't know why I did it backwards.
What? Yeah, I was gonna say. What?
Yeah, t over n, you'll literally just have it as your p, your e, the rate of increase. So if it's an increase of 3%, you would just literally put it down as 0.3 because they're saying here it's a 3% growth. And you literally put down how many days you want it to grow. So if this grows 5% every year, you're going to do this times your 5 years. So this is another way of doing it without having like a weird fraction here as your growth rate. Does that make sense? Cool.
Yeah.
So there's two ways to do that. You can do it as this, or you can do it as P 1.01 uh 5 over 1 because it's every year. All right. So now moving on to here. So now we're going to do problems with continuous growth. So go to this store. So they want us to actually go into this website to figure it out. So what are we doing here? So we're doing 1900 to 99. So we're going to go to, do they even have the years that they want anymore?
I don't think so. The page is not working.
Oh, wow. So they don't have the actual years, guys. So let me see if I can look it up. US Census Bureau. We might have to Google this. US Census Bureau. It would help. It would help if I actually copied the right thing.
Yeah, that would be nice. Why don't you just do it normally, like Control C in this,
That's what I
Control B?
that's what I did right now.
Apparently, you just gotta click on it.
Census Bureau 1900 to 1999. I think this is going to take me to the exact same website. Oh wait, we did it. um so when I put this on YouTube, I'll probably link this website in the comments for you guys to refer to in the future. But what we're gonna do here is we're gonna figure out the rate. Really not okay. Resident. Okay, I was really worried. I was like, well, this isn't gonna help if it's not applicable. So we're gonna use these values: the population and the population up to. Well, it looks like it doesn't have 1999, so it looks like we're gonna have to settle for 1998. All right. So here we're going to do to record the national population of the United States in 1999, find the average percentage of growth. So if we're finding the average percent of growth, what it's asking us to do is, let's say we have a graph here. We start off at 1999, and then we're here at 1998 in this case. It's basically asking us to find the slope. So our population with growth could have been like this, but it wants us to find the average rate of change, which is the same thing as finding the slope from, oops, this is 1990, from here to here. So when we're calculating this out, we just use the slope formula. So we go to the equation editor. We want to put our y values on the top because it's always rise over run. So fraction rise divided by run. And then here we're going to put, delete this one because this one's not useful anymore. We're going to put this, so I'm just going to copy it. I'm just going to do what Garrett said and just hit Control C. Where is it? There it is. Minus this. And the run's going to be 98 years because of the fact that it's from 1998 to 1900. And then we're just going to calculate this out. So let me pull out my calculator. So, so we have about 194,205. So again, make it a fraction. 194,205. 194,205. We're going to divide this by the 98. I guess if you really want to show your work, technically you can do this, not times. So in other words, what we're going to do, I mean, you guys know how to calculate slope, right? Yes, no, maybe? Okay. Good enough for me. So 1,980, let's say 82. So every year it's going down about 1,982. 1,982. If you submit it, I think it says something like answers may vary. Oh, yeah. So they have like, what is this? Annual percentage rate of change. What? Oh, they want us to figure out the percentage. So then we're going to take this number because they want us to find the actual percentage. So we're going to take this 1982 and divide this by the initial population, which was 76094. So we're going to take this number, 192. That was my bad, guys, for not reading the question all the way through. Remember to read your questions on the test. Otherwise, you can make a mistake. So I'm getting about a 2% growth rate. The reason why my percentage is different than theirs is because they had another year. So it probably grew a lot within that last year. So, but we're going to use this percentage to kind of continue it. So every year we're talking about find the average percentage growth. Okay. So what was it? 2.6? 2.6%. 2.6%. Assuming that the population growth remains constant, right in exponential rate for years after that. So if we're looking for an average growth, we're going to do equation editor. P subscript T equals, where's my equal sign? Equals P, and they're talking about after that year. So I'm going to do it starting from the year that we want. So P naught, well, let me just do P naught first. So P naught, and then our rate of change. So do they want it continuous growth? Remains constant, population growth, number of years after that. So E, I'm going to assume they want it as a regular growth because they didn't really tell us. So here we're going to get this, that. We're going to raise it to the exponent, make this exponent a fraction. And, oh, actually, we don't even have to make it a fraction because it's talking about every year. So they wanted us to do it every year. So we're going to put this as T. And it's going to be, technically, it's going to be T minus 1998 because they want it for years after 1998. Does that make sense?
Yeah.
So this is technically how we would write down our answer. Let's see how Admentum wants it. So they want it, oh, they wanted it with this. So if they want it as an exponent, when you edit this, you would put the E, you would put the point 026. So basically, because their numbers are different than ours, we would write it down as P of T equals our starting population, which they want the actual starting population of 1998. So we would do, not that one, sorry.
This one is so long. I just
Did you guys kind of like space out?
knowing it, yes. Now, no. Yes.
Okay, so let's do kind of like a mental reset. Everybody gather themselves, even people watching at home. So, so when we're doing this, guys, we want to kind of see what our population starts at. So if we want to do what our population starts at, our number, the number I got was this right here. They're getting this number because I don't know how they got access to it, but they somehow got access to 1999, and I don't have 1999 on this list. So I find that weird, especially because it says 20th century. I'm like, last time I checked, 1999 is in the 20th century. But so we're going to put down the population at 1999. It's going to be an exponent, and this is going to be our percentage. Does that make sense? That looks terrible though. And the key thing here, the reason why I messed up is they wanted the growth rate in a percentage. So I calculated the actual rate per year. They wanted it as a percentage, so they had to take the number I got here and divide it by the starting number over here. Does that make sense? Oh, and average since 1999. So technically, we're supposed to do it from this one. Oh, that's why they got such a small number. Does that make sense? I know I kind of just realized I did it wrong, but So they wanted this. They wanted this 1982 divided by 270299. So that's why they get like a per 0.9%. I got 0.7 because again, this number is different than the number they got. Make sense? Yes, no, maybe. More confused now?
Quite simple.
Okay. All right. So now we're going to use this equation to figure this out. So year, so our T is going to be this 2011. So we're going to do this. We're going to subtract this out. So that's going to give us a T of 13. Does that make sense? And then when we input this in, we're going to put this in as P of, they say T, it's technically supposed to be 11 because our T is 11 years. We're going to do our exponential growth. Oh, sorry, our initial population. Sorry. Yeah, I forgot the initial population. What was our initial population? So here's our initial population. I'm going to do this instead of typing. Did you guys prefer when I write it or when I type it out?
Honestly, it doesn't really matter to me. But you spelling it, you doing it like as on pen,
Uh huh.
the pen, honestly is way better because it's just like it's like almost doing direct like teaching.
Okay, I'll do it on pen then because I think it slowed me down when I was typing it all up. And then what you guys can do if you guys don't want to show all your work like this, remember you can always create a Google Doc and just put the link in here. Do you guys know how to make a Google Doc and post the link in? No? Okay. So if you want to make a Google Doc, what you do is you go to doc Google.
No, I remember how to do this for child and parenting.
Okay.
I remember how to do this for my child and parenting unit.
Okay.
Just know another.
One thing to do too to make sure any teacher can see it, not just me, is when you go to share. So click share. When you click share, oh, make sure you name your document. When you click share, make sure to change it from restricted so that anyone can see it. So if you click that thing to change, now anybody in OFL can see it so long as they have the link. So you're gonna copy the link here, and then just paste it in here, and anybody can see any of your pictures you have on that doc. So, so make sure that you're putting your pictures in here. Otherwise, you're going to give me a doc to a blank link. Does that make sense? Cool. I like doing it that way. That way you can write it on paper and then or screenshot it or whatever. Like if you have like a stylus or anything, write it on what write it on whatever you have, and that'll help you out. So we're gonna get that. What was our rate of growth? Like 0.0%? It was 0.7. Thank you. 0.7%. 0.7% growth rate, or in other words, because we can't put percent signs in there, make sure you put that down as 0.007. And the amount of years is going to be times 13. So using the equation, did they want us to actually figure it out? Yep, they want us to figure it out. So hold up while I pull out the big calculator. Or you know what? Let me show you guys how to do it on Google.
Baddest calculator in the world.
No, I mean it kind of is. I'll show you when it actually opens up. You can use it on Google, but I'm not the biggest fan of the Google. Or oh, they have a calculator on Desmos. Ooh. Oh, guys, you can use a scientific calculator on Desmos. If you don't have one at home, go to desmos.com/scientific. So let's try this out. 75. What was our initial population? Oh, 270. Oops. 270, 299. E. Where's the E? Function. E. And you said the growth rate was 0.7%, Nick? Okay. And then we're going to multiply that by 13 years. Oops. Try to make sure your thing's still up here when you do the time sign. Why is it not letting me do the times? Okay. So for some reason, I had to put the 13 over here and then put the times. I don't know why. That was weird. And you hit enter, and you get nothing. All right. So let's do it on a real calculator. I mean, it's a pretty big boy, I guess. I mean, this is supposed to be the screen. So remember those scientific calculators at school, guys? This is supposed to be that. E. This is supposed to be 0.007 times 13. Hopefully, this calculator can handle it. This calculator can handle it. So. So if you guys are having trouble, you might want to find like a scientific calculator online that's not Desmos apparently. Sorry about that. I was excited. I was like, "Ooh, they have a calculator on Desmos," and then 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 it didn't work. So then this will tell us how much the population is. So it went up by like 20,000, which I feel like I think they're doing these in the millions or something because I'm like, I could have sworn the population of the United States was bigger than this. Prior to that, the total population. I feel like this has to be in the thousands because I thought we were like at like a million people in the United States, but maybe I'm wrong. All right. So, does anybody have any questions on how to figure that out? No. All right. So here, like I said, it is going to be a little off because I'm not working with their numbers. They had a higher starting rate, for example, and their population growth was a lot more. So that's how come our numbers are a little off, but that's how you would set it up for an exponential growth. Complete the web search. So now we want to look for the population in 2011. So again, just go to Google US population 2011. So yeah, that's what I thought. We were in the millions. That's why I'm really confused at what we're doing on this. Like I said, I think these numbers, where are they? Where'd the numbers go? I want to say these numbers are in the thousands. So we are off by not that much because I want to say if these are in the thousands, then this would end up being that much. So we're only off by like what, 40 million, which I know seems like a lot. Um, but as far as significant digits goes, we're only off by like 40 digits. Does that make sense? And and that makes sense because this was 9 years ago. So it's almost another, like, if we look at our population graph, this went up by like 20,000, right? And if we do another like 13 years, that should also be another 20,000. So yeah, that makes sense. So if we add 20,000 to this number, yeah, we're about, what was that number again, Nick? 331 million. Yeah, so it went up by 20 million again. So yeah, it looks like we are like at a fairly consistent growth rate. Sadly.
Sadly.
Population, blah blah blah. Explain the differences. So so we can explain the differences just by like we can literally say things like changes in the economy because technically it should have gone up exponentially, but in the middle between 1999 and 2011 there was a housing crisis right here in 2008, so that probably decreased the growth a little bit. And there's other factors. There's like a lot of reasons why the fact that it grows exponentially instead of linearly, things like that. So just add all that stuff in there. But we were actually pretty close on that one. Um, so let me see how much what's next. I think that's a good place for us to leave off. Do you guys have any questions on how to set up exponential models or anything like that?
Not yet.
I'm gonna stop the recording.